along the wild, untamed coastline of the Pacific Northwest, where ancient forests meet the relentless Pacific, a colossal force lies hidden beneath the waves. Stretching from the shadowy depths off Northern California to the mist-shrouded shores of Vancouver Island, this force is not merely a feature of the landscape, it is the landscape's architect, sculpting mountains, valleys, and the very sea floor itself. Beneath the ocean's surface, two titanic slabs of the Earth's crust, the dense Juan de Fuca plate and the vast North American plate, are locked in a silent, inexorable contest. The Juan de Fuca plate, born from the fiery mid-ocean ridge, is forced eastward, plunging beneath its continental neighbor in a process known as subduction. Over millions of years, this relentless descent has forged the Cascade Range, towering volcanoes and rugged peaks that rise as monuments to the ceaseless collision below. Yet, the process is anything but smooth. The plates do not glide past each other. Instead, they catch and grind, their boundaries twisted and deformed by unimaginable pressures. For centuries, the boundary has remained locked, the plates fused by friction so intense it halts their movement. The ocean floor itself is warped and buckled, its sediments compressed and folded into vast underwater ridges and deep, shadowy trenches. The Juan de Fuca plate continues its relentless push, forcing the North American plate to bend and flex. The seafloor above bows upward, storing energy like a colossal spring wound, tighter with every passing year. This quiet tension is deceptive. The ocean's surface may appear calm, but deep below, the crust is straining, the energy mounting in silence. The Cascadia Subduction Zone is not like the restless faults of California, which shudder and slip in frequent, smaller quakes. Here the silence is profound, the pressure building for centuries. The Pacific Rim is encircled by subduction zones, arcs of geological instability known as the Ring of Fire. In places like Japan and Chile, these zones rupture frequently, unleashing the planet's fury in earthquakes and volcanic eruptions. But Cascadia remains ominously still. The ocean floor here is a realm of contrasts. Serene on the surface, yet beneath, the rocks are twisted and fractured, ancient faults etched deep into the crust. Hydrothermal vents spew mineral-rich water, and cold seeps nourish unique ecosystems, all shaped by the slow violence of tectonic movement. Along the subduction zone, the seafloor is marked by dramatic features, towering ridges, deep troughs, and scarps where the plates have wrenched the crust apart. These underwater landscapes are silent witnesses to the immense forces at work, their forms sculpted by the slow accumulation of strain. The strain continues to build, year after year, century after century. When the locked plates finally slip, the energy released will be catastrophic, a megathrust earthquake, sending shockwaves through the crust and unleashing tsunamis across the Pacific. Scientists estimate that the next rupture could reach a magnitude of 9 or greater, rivaling the most powerful earthquakes ever recorded. The last event, over 3 centuries ago, left its mark in the geological record. Ghost forests drowned by sudden land subsidence, and sand layers deposited by ancient tsunamis. Since that ancient upheaval, the pressure has mounted in silence, the clockwork of geology ticking inexorably forward. The ocean floor continues to deform, the plates remain locked, and the energy accumulates, unseen but ever present. The question is not whether the sleeping giant will awaken, but when. The Pacific Northwest stands poised on the edge of a geological reckoning, its fate shaped by the slow, relentless dance of the Earth's hidden forces beneath the waves. To truly grasp the magnitude of the threat facing the Pacific Northwest, we must turn to the landscape itself, where the past is etched into the very bones of the Earth. Along the rugged coasts of Washington and Oregon, nature has preserved a haunting record of catastrophe. Here, the land tells a story that predates written history, a story written in wood, water, and earth. These are the ghost forests, vast stands of long-dead trees, their trunks rising eerily from tidal marshes and estuaries where living forests cannot survive. The remains of ancient cedar and spruce, preserved by salt and silt, stand as silent witnesses to a world transformed in an instant. These trees did not die slowly, nor did they fall to disease or fire. Instead, they were killed suddenly, their roots drowned by a surge of salt water that forever altered the landscape. The ghost forests are more than a curiosity. They are a geological archive, preserving the moment when the land itself was violently reshaped. By analyzing the growth rings of these trees, scientists have unlocked a timeline of environmental change. Each ring records a year of life, and together they reveal a sudden, simultaneous death across hundreds of miles of coastline. The evidence is unmistakable. In the late summer or autumn of 1699, every tree in these forests died at once. The cause was not fire nor blight, but a catastrophic event that struck the entire region. The absence of burn marks or rot rules out the usual suspects. Instead, the tree's preservation points to a sudden environmental upheaval. The only plausible explanation is a dramatic subsidence event, where the ground beneath the forests abruptly dropped, in some places by as much as 2 meters. This sudden sinking allowed the Pacific Ocean to surge inland, flooding the forests with salt water and suffocating the trees' roots. The transformation was immediate and irreversible. Such a dramatic change is the unmistakable fingerprint of a massive subduction zone earthquake, an event where the Earth's crust is forced downward as tectonic plates suddenly slip. For centuries, the North American plate is squeezed and bulges upward along its western edge. When the pressure is finally released, the land collapses, lowering the coastline and triggering environmental chaos. The result is a landscape forever changed, forests drowned, shorelines redrawn, and the memory of disaster preserved in the very wood of the trees. Today, the ghost forests stand as natural monuments to the last great Cascadia earthquake, their presence a warning written in the language of geology. The rings of these trees not only pinpoint the year of the disaster, but also provide a precise record of how quickly the land can be transformed by seismic forces. The scientific significance of the ghost forests extends far beyond the Pacific Northwest. Their story is a crucial piece of the global puzzle of earthquake science, linking local evidence to worldwide seismic events. The environmental changes recorded in these forests are echoed across the ocean, where a mysterious tsunami struck Japan in January 1700. An event with no local earthquake to explain it. Japanese records describe a devastating wave arriving without warning, its origins a mystery for centuries. Only by combining the evidence from the ghost forests with these historical accounts did scientists uncover the truth. The Cascadia Megaquake sent a tsunami racing across the Pacific, linking 2 continents in disaster. The ghost forests, preserved in salt and silence, are more than relics of the past. They are a living warning, evidence that the land can change in an instant and that the next great earthquake is not a question of if, but when. Along the Pacific Northwest coast, the silent sentinels of ghost forests stand as a stark reminder of sudden, catastrophic change. But the true chronicle of ancient earthquakes is written far beneath the waves, in the quiet, undisturbed layers of mud and sand that blanket the ocean floor. Here, each layer of sediment is a page in a geological diary, recording the slow accumulation of silt, clay, and organic matter over thousands of years. These layers are undisturbed except when extraordinary forces, like a megathrust earthquake, sweep across the seafloor. When geologists extract long cylindrical cores from the seabed, they reveal a striking pattern, alternating bands of dark, fine-grained mud and lighter, coarser sand. The dark layers represent years of calm, steady deposition. The pale, sandy bands are abrupt, chaotic, evidence of violent underwater avalanches called turbidity currents. These turbidity currents are triggered when the seafloor is jolted by a massive earthquake, sending clouds of sand and debris racing downslope. The resulting sandy layers are deposited in a matter of hours, sharply contrasting with the centuries of slow mud accumulation above and below. By carefully counting and dating these sandy layers, scientists have reconstructed a timeline of megathrust earthquakes stretching back over 10,000 years. Each sandy band is a fingerprint of a seismic catastrophe preserved in perfect sequence. The clarity of this record is astonishing. It reveals that the Cascadia Subduction Zone has unleashed at least 19 earthquakes of immense magnitude, each one powerful enough to reshape the coastline and send shockwaves across the Pacific. To complement the story told by the mud, scientists deploy high-precision GPS instruments across the region. These devices measure the slow, relentless movement of the Earth's crust, detecting shifts as small as a few millimeters per year. The data reveal a continent under stress. The North American plate is being compressed and pushed eastward, while the coastal margin is gradually uplifted, storing energy like a wound spring. This deformation matches the predictions of geological models and confirms what the sedimentary record has already shown. The region is locked in a cycle of strain and release, with each earthquake resetting the clock. Today, with every new core sample and every GPS reading, we are not only uncovering the history of past megathrust events, we are witnessing the slow, silent build-up to the next one, written in the language of mud and motion beneath our feet. The story of the Pacific Northwest's seismic future is written not in hours or days, but in the slow, relentless language of geology. Ghost forests, sediment cores, and GPS data together reveal a landscape shaped by cycles of violent upheaval and long, deceptive calm. The Cascadia Subduction Zone, where the Juan de Fuca Plate dives beneath the North American plate, is a crucible of tectonic energy. Here the Earth's crust is forced downward, accumulating strain over centuries, an invisible process, but one that leaves subtle fingerprints in the land. Scientists have pieced together the region's seismic history by reading these clues. Tree rings in ghost forests record sudden land subsidence. Sediment layers in coastal marshes show abrupt, tsunami-driven deposits. GPS stations, anchored deep in bedrock, measure the slow, almost imperceptible westward drift of the continent as strain builds. The geological record tells us that, on average, a full rupture, magnitude 9 earthquake occurs every 5 to 6 centuries. Smaller, yet still catastrophic, magnitude 8 events may happen every 240 years. The last full rupture event struck in the year 1700, leaving a trail of destruction from Vancouver Island to northern California. As of 2026, 326 years have passed since that last great quake. This number is not just a statistic, it is a warning. We are now well within the window for the next major event, and the average recurrence interval for a magnitude 8 has already been surpassed. But the Earth's clock is not a metronome. The intervals between past earthquakes have varied wildly, sometimes as short as 200 years, other times stretching to 1,000. This irregularity is rooted in the complex physics of tectonic stress, accumulation, and release. Deep beneath the surface, the subducting plate grinds inexorably forward, its leading edge locked against the overriding plate. Over centuries, stress accumulates along the fault, like a spring winding tighter and tighter. Eventually, the frictional resistance is overcome, and the fault slips in a sudden, violent release, an earthquake. Predicting exactly when this will happen is one of science's greatest challenges. While GPS and satellite data can track the rate of strain accumulation, and seismographs can detect microquakes and tremors, there is no reliable precursor that signals the imminent arrival of a megaquake. The system is chaotic, influenced by countless variables: rock composition, fluid pressure, fault geometry, and even the after-effects of distant seismic events. Some segments of the fault may creep slowly, releasing energy without major earthquakes. Others remain locked, storing ever more potential energy. The transition from locked to slipping is abrupt and unpredictable, governed by processes that unfold at the molecular scale within rocks miles beneath our feet. Scientists use probabilistic models to estimate the likelihood of future earthquakes, but these are based on averages and statistical patterns, not certainties. Each passing year without a major event increases the probability, but does not guarantee when the rupture will occur. The geological debt is mounting, the plates are locked, the pressure is building, and the historical record shows that a release is inevitable. The period of quiet we have enjoyed is not the norm, it is a temporary pause in a much longer cycle. The Earth's unpredictable clock continues to tick hidden beneath the forests, mountains, and coastlines of the Pacific Northwest. It is a clock with no visible hands, no audible chime, and no promise of warning before it strikes. For all our scientific advances, the precise moment of the next great earthquake remains unknowable, a testament to the complexity and power of the planet we call home. When the Cascadia Fault finally ruptures, the event will ignite at a single, invisible point deep beneath the Pacific, far from the city's skyline. From this origin, a rupture will race along the fault line at several kilometers per second, sending seismic shockwaves surging toward the urban coast. If the entire 1,000-kilometer fault gives way, the city will not endure a brief jolt, but a relentless, rolling upheaval that could last 3, 4, or even 5 minutes, an eternity for the built environment. During this prolonged assault, the city's infrastructure will be subjected to forces far beyond what most structures were ever designed to withstand. Steel beams will groan and twist, bolts may shear, and glass curtain walls will flex and shudder, with panels popping from their frames as the city's skeleton is tested to its limits. Inside empty office towers, ceiling grids will collapse, light fixtures will swing and crash, and the contents of entire floors will be tossed and scattered. The city's power grid will flicker and fail as substations spark and transformers explode, plunging entire districts into darkness even as the ground continues to convulse. Seattle, built atop a deep, sedimentary basin, will experience seismic waves that become trapped and amplified, causing the ground to behave like a bowl of jelly beneath the city grid. The ground will undulate, rippling beneath entire neighborhoods, distorting streets and foundations as if the city were afloat on a restless sea. Seismic energy will reverberate within the basin, amplifying both the intensity and the duration of the shaking, with the city center enduring the harshest punishment. Compared to outlying areas built on solid bedrock, the city's core will shake more violently and for much longer, making it a focal point for destruction. The contrast will be stark. While some neighborhoods experience moderate tremors, others will be subjected to catastrophic sustained motion. Unreinforced masonry buildings, their brick facades and mortar joints brittle with age, will crack and collapse, sending debris cascading into empty streets and alleys. In historic districts, entire blocks may be buried beneath clouds of dust and heaps of rubble, transforming familiar landmarks into impassable wastelands. Modern skyscrapers, engineered for flexibility, will sway by meters at their summits, their support columns and expansion joints pushed to the brink. Designed for brief shocks, these towers will be forced to endure a relentless 5-minute onslaught, risking structural fatigue, warped elevator shafts, and catastrophic mechanical failures. While most may remain standing, many will be left irreparably damaged, with shattered glass raining down and facades stripped bare. Parking garages may pancake, and underground utility tunnels will buckle and rupture, flooding streets with water and sewage as pipes burst beneath the surface. Ruptured gas lines and electrical shorts will ignite fires that spread unchecked through debris-littered blocks, compounding the devastation. Inside commercial and industrial spaces, equipment will topple, glass will shatter, and ceilings will collapse, leaving interiors in total disarray. Roads and highways will crack and buckle, while bridges, the vital arteries of the city, will twist and strain, their expansion joints separating and decks splitting open. Many older bridges and overpasses will fail, collapsing into rivers or blocking intersections, severing critical transportation routes. Water towers may topple, reservoirs could crack and drain, and communication towers will bend or collapse, plunging the city into silence and isolation. The very ground itself will fracture and heave, opening fissures in pavement, dislodging manhole covers and transforming the city's foundation into a violent, unpredictable enemy for nearly 5 endless minutes. Among the most extraordinary and perilous phenomena unleashed by a megaquake is soil liquefaction, a process that transforms solid ground into a churning, unstable slurry. Liquefaction occurs in regions where the earth is composed of loosely packed, water-saturated sediments, such as river deltas, coastal plains, and reclaimed land. Here, the soil structure is fragile, with grains barely held together by friction and the buoyant force of groundwater. When seismic waves from a major earthquake ripple through these layers, the violent shaking causes the water pressure between soil particles to spike. The grains lose contact, and the soil abruptly loses its ability to support weight. The ground surface may begin to ripple and undulate as if it were breathing. Cracks open and sand boils. Fountains of water and sediment erupt from below, marking the dramatic failure of the Earth's structure. In these moments, the landscape is transformed. What was once firm ground now behaves like quicksand, unable to bear the weight of anything above. Roads and embankments buckle and sink, their engineered surfaces no match for the liquefied soil beneath. Entire stretches of infrastructure can be swallowed as the ground gives way. Beneath the surface, the consequences are equally severe. Underground utilities, water mains, gas lines, and electrical conduits are stretched and snapped as the soil shifts and flows, severing lifelines essential to urban function. Industrial zones, often built on reclaimed or low-lying land, are especially vulnerable. Massive storage tanks and warehouses, once stable, may tilt or collapse as their foundations are undermined. In Portland, the critical energy infrastructure hub sits atop such treacherous ground. During a megaquake, the soil beneath these tanks could liquefy, causing catastrophic ruptures and the uncontrolled release of fuel. The result would be a rapid spread of hazardous materials into the river system, triggering an environmental disaster that could persist for decades. Even the riverbanks themselves are not immune. As the soil liquefies, entire sections may slump into the water, altering the river's course and sending plumes of sediment downstream. Bridges spanning these unstable zones face grave danger. Their supports, once anchored in solid ground, may suddenly lose purchase, causing spans to tilt, crack, or collapse. In the aftermath, the landscape itself is forever changed. Patches of land may be left sunken or elevated, new channels carved by redirected water, and the familiar contours of the city and countryside reshaped by the forces unleashed below. As fuel and chemicals spread across the water's surface, the risk of ignition grows, threatening to turn the river into a corridor of fire. Downed power lines, brought low by the same ground failure, dangle perilously close to the contaminated water. A single spark could ignite the volatile slick, setting off a chain reaction of destruction that spreads far beyond the initial quake. The river, now a channel of flame, would consume bridges and infrastructure, compounding the devastation. This is the terrifying reality of liquefaction, a cascade of failures, where the transformation of the land itself amplifies the destruction, leaving a landscape unrecognizable and a city struggling to survive. As the relentless shaking finally ceases, the ocean itself becomes the stage for a new and extraordinary display of nature's power. The colossal shift of the seafloor, sometimes rising by tens of meters over an area the size of a small country, displaces an immense volume of water in an instant. This abrupt vertical movement acts as a titanic paddle, sending a pulse of energy through the water column. The ocean, forced upward, forms a series of long, low waves that radiate outward at jetliner speeds, sometimes over 700 kilometers per hour in deep water. As these waves approach the shallower waters near the coast, their speed decreases but their energy compresses, causing the wave height to grow dramatically. The first visible sign is often the ocean's sudden and unnatural retreat, a rapid withdrawal that exposes the seafloor, revealing rocks, shells, and marine life rarely seen by human eyes. This is not a low tide, but the ocean gathering its strength. The water draws back, sometimes hundreds of meters, leaving the land eerily silent for a brief, tense moment. Then, with unstoppable force, the tsunami arrives, not as a single wave, but as a series of surges, each one a fast-rising wall of water. Unlike ordinary waves that break and curl, a tsunami surge is a churning, debris-laden mass, its leading edge rising rapidly and advancing with the speed of a sprinting animal. The height can reach 10, 20, or even 40 meters in exposed locations, towering over the landscape like a moving cliff. The tsunami does not stop at the shoreline. Its immense momentum drives it far inland, sweeping across beaches, fields, and forests, scouring the earth of soil, vegetation, and anything in its path. The force of the water is enough to uproot trees, strip away topsoil, and reshape the very contours of the land. In the aftermath, the landscape is transformed. Where once there were roads, forests, and buildings, there may be only bare earth and tangled debris. The tsunami's power is recorded in the layers of sand it deposits far inland. Ocean sand with no natural reason to be there, buried beneath the soil as a silent testament to the water's reach. These sand layers, discovered by geologists, are the fingerprints of past tsunamis. They reveal how the ocean's fury has repeatedly swept far beyond the shore, leaving behind a record of destruction and renewal that endures for centuries. The scars on the land, the ghost forests, and the buried sand all tell the same story. When the ocean retreats, it is only to return with unimaginable force, reshaping the coastline and leaving a legacy that will be read by future generations. In the wake of a full-rupture Cascadia Megaquake and tsunami, the Pacific Northwest would be transformed beyond recognition. The landscape itself would bear the scars of unimaginable violence, forests flattened by landslides, hillsides stripped bare, and entire river valleys choked with debris. The coastline would be dramatically reshaped. Tsunami waves would carve new inlets, erase beaches, and leave behind sandbars where neighborhoods once stood. Cliffs would collapse into the sea, and estuaries would be clogged with the remnants of both natural and human-made structures. Inland, the force of the quake would trigger massive landslides, sending millions of tons of earth tumbling down mountain slopes. Rivers would be dammed by debris, creating new lakes and flooding valleys that had never before seen standing water. Agricultural fields would be buried under layers of silt and rubble, their irrigation systems shattered. The region's once fertile soil would be contaminated by saltwater intrusion and chemical spills from ruptured industrial sites, threatening harvests for years to come. Infrastructure would be left in ruins. Highways and rail lines would be twisted and broken, with entire sections sunken or uplifted by the shifting earth. Power transmission towers would lie toppled across the countryside, and substations would be flooded or destroyed, leaving vast areas without electricity. Water systems would fail as reservoirs cracked and treatment plants went offline. Rivers, now blocked or redirected by landslides, would flood new areas and leave others parched. The contamination of water sources would pose a long-term threat to both human and ecological health. The region's industrial zones would become environmental hazards, with chemical spills and fires polluting air and water. Oil slicks would drift down rivers, and plumes of smoke would rise from damaged refineries and power plants. The ecosystem would be thrown into chaos. Wetlands and estuaries, vital habitats for countless species, would be inundated with salt water and debris. Fish kills would blanket the surface of rivers and bays, while wildlife would be forced to flee or adapt to radically altered environments. In the months and years that follow, invasive species would take root in the disturbed soil, outcompeting native plants and further destabilizing the ecosystem. Forests would struggle to recover, their regrowth hampered by erosion and the loss of topsoil. the scars of the disaster would persist for generations. New lakes and landslide-dammed rivers would permanently alter the hydrology of the region. Some coastal areas would be lost to the sea forever, while others would slowly be reclaimed by nature in unfamiliar forms. The Pacific Northwest, once defined by its lush forests, fertile valleys, and vibrant coastline, would become a landscape of ruin and transformation, a stark reminder of the power of the Earth and the fragility of the world we build upon it. The threat of a Cascadia Megaquake is daunting, but science and innovation have transformed how we prepare, respond, and recover from such catastrophic events. Today, state-of-the-art monitoring centers track seismic activity in real time, while engineers use robotics and virtual reality to test and improve the resilience of critical infrastructure. The Shake Alert Earthquake Early Warning System stands at the forefront of disaster technology, instantly analyzing seismic waves and broadcasting alerts across a vast digital network. A dense web of seismometers, satellites, and high-precision sensors detects the earliest tremors, transmitting data in milliseconds to centralized hubs. Advanced algorithms distinguish between harmless P waves and the destructive S waves that follow, allowing for rapid, automated decision-making. This technology creates a critical window, sometimes up to several minutes, enabling automated systems to initiate citywide safety protocols. Automated responses include securing hazardous materials, activating fire suppression, and halting elevators to prevent entrapment. Gas pipelines and electrical grids are remotely shut down, reducing the risk of fires and secondary disasters. High-speed trains and transit systems are brought to a safe stop, guided by real-time data and predictive modeling. In hospitals, automated protocols pause surgeries and secure sensitive equipment, protecting both patients and staff. Mass notification systems instantly reach millions, providing clear, actionable instructions through every available channel. In cities like Seattle, advanced modeling predicts wave arrival times and identifies optimal evacuation routes, maximizing every second of warning. Smart buildings unlock emergency exits and monitor structural integrity, while drones assist in real-time evacuation management. For coastal regions, tsunami modeling and automated siren networks provide critical guidance for rapid evacuation. Where horizontal evacuation is impossible, vertical evacuation towers, engineered to withstand both quake and wave, offer life-saving refuge. These structures are rigorously tested and strategically placed, providing elevated safety for entire communities. Acosta Elementary School in Westport, Washington, is a pioneering example. Its reinforced rooftop designed to shelter over 1,000 people above the reach of the waves. These refugees are engineered for rapid access and maximum capacity, ensuring survival even in the most extreme scenarios. As more communities adopt these innovations, North America is setting new standards in disaster resilience. The Pacific Northwest's future is inseparable from the Cascadia Subduction Zone, a dynamic boundary that shapes both risk and opportunity. When the great earthquake strikes, automated systems will assess damage, prioritize rescue, and coordinate resources for rapid recovery. Recovery will be driven by science, through resilient design, rapid reconstruction, and adaptive urban planning. Every retrofitted building, every optimized supply chain, and every community-wide drill is a testament to human ingenuity and foresight. Modular shelters, clean water systems, and renewable energy microgrids ensure that even in the aftermath, communities can recover swiftly and sustainably. The Earth's forces are inevitable, but with relentless scientific progress and strategic preparedness, we can transform disaster into survival and survival into resilience. Beneath the lush forests and rugged coastline of the Pacific Northwest, colossal forces are constantly at work, unseen but ever present. At the heart of this region's seismic volatility lies the Cascadia Subduction Zone, a vast tectonic boundary stretching nearly 700 miles offshore. Here, the immense Juan de Fuca Plate, a remnant of an ancient oceanic slab, relentlessly plunges beneath the much larger North American plate. This slow-motion collision is measured in mere inches each year, but over centuries it stores titanic amounts of energy. The subduction process is far from smooth. Friction locks the plates together, causing stress to accumulate along the boundary. Deep beneath the ocean floor, the descending plate carries water-rich sediments into the mantle, where high temperatures and pressures cause minerals to release fluids. This weakens the overlying rock, promoting melting and fueling the region's chain of volcanoes, from Mount St. Helens to Mount Rainier. But the most dramatic consequence unfolds at the locked interface. As stress intensifies, the crust bends and deforms, silently warping the landscape above. When the accumulated strain surpasses the strength of the rocks, the boundary ruptures in a violent release, an earthquake. Energy radiates outward in seismic waves, shaking the ground and reshaping coastlines in mere moments. The Cascadia Subduction Zone is a classic example of a megathrust fault, capable of producing some of the largest earthquakes on Earth. These events not only generate intense ground shaking, but also displace vast volumes of seawater, spawning tsunamis that race across the Pacific. Elsewhere, the Pacific Northwest is crisscrossed by secondary faults, fractures born from the stresses of the subduction process. These faults, both onshore and offshore, create a complex seismic landscape where the Earth's crust is perpetually stretched, compressed, and broken. This dynamic tectonic engine is responsible for sculpting the region's mountains, forging deep offshore trenches, and fueling volcanic arcs. It is a process measured not in years, but in millennia, shaping the landscape with every silent shift and every explosive rupture. In the Pacific Northwest, the ground beneath our feet is not static, but alive with the ceaseless motion of planetary forces. Though invisible to the eye, these engines below are the architects of both beauty and hazard, a reminder that the Pacific Northwest sits atop one of the most powerful tectonic theaters on Earth. Far from the roar of crashing waves or trembling earth, the Pacific Northwest holds secrets written in the language of stone, sand, and silt. The true story of ancient megaquakes is not told by eyewitnesses, but by the silent geological evidence left behind. Clues painstakingly revealed by scientists who read the landscape like a history book. One of the most telling signatures is fossilized tsunami deposits. Along the quiet fringes of coastal marshes and estuaries, thin layers of ocean sand can be found, buried beneath centuries of peat and soil. These sands, often just a few inches thick, are foreign intruders, washed far inland by the force of ancient tsunamis. Within them, tiny marine shells and diatoms mingle with land plants, a jumbled testament to the power of a wave that once swept across the land. By dating the organic material above and below these layers, researchers have pieced together a timeline of catastrophic events, some stretching back thousands of years. Elsewhere, uplifted marine terraces stand as silent monuments to the Earth's restless power. These broad, flat platforms were once beaches, washed daily by the tides. But megaquakes have thrust them upward, leaving them stranded high above the modern shoreline. The terraces weather slowly in the coastal wind, their ancient shells and barnacles now far from the sea, marking the moments when the land itself leapt skyward. Even the trees bear witness. In certain ghostly forests, the trunks of long-dead cedars and spruces protrude from tidal mudflats, their roots preserved in salt and silence. These trees died suddenly, their roots drowned when the land abruptly dropped during a great earthquake, letting the sea rush in. Their preserved stumps, radiocarbon dated and aligned with tsunami deposits, help reconstruct the sequence and scale of past disasters. Beneath the surface, cores of mud extracted from lakes and riverbeds reveal subtle layers of disturbance, fine sediments shaken loose by seismic waves or sudden influxes of sand from ancient tsunamis. Each layer is a silent record, a timestamp of catastrophe. Together, these scattered clues form a mosaic of evidence, proof that the region has been shaped and reshaped by a cycle of seismic upheaval. The landscape itself is a living archive, holding messages from the ancient earth waiting for those who know how to read them. In the shadow of ancient disasters, the modern world has turned to science and engineering to confront the threat of megaquakes. Across the Pacific Northwest and other seismic hotspots, the landscape is quietly transforming, not with monuments or memorials, but with a new generation of resilient infrastructure designed to withstand nature's fury. At the heart of this revolution is base isolation technology. Unlike traditional buildings anchored rigidly to their foundations, structures with base isolators rest atop flexible bearings, giant rubber and steel pads that absorb seismic energy. When the ground shakes, these isolators allow buildings to glide back and forth, dramatically reducing the forces that reach the structure above. The result: critical hospitals, emergency centers, and bridges remain standing, even as the earth convulses beneath them. Elsewhere, engineers are reimagining skyscrapers with tuned mass dampers, massive counterweights, often hidden near the top floors, that move in opposition to seismic vibrations. When a quake strikes, these dampers sway out of phase with the building, cancelling out some of the destructive motion. This innovation, combined with high-strength, flexible materials, helps tall structures bend without breaking, safeguarding the lives and assets within. Bridges and overpasses, vital arteries for rescue and recovery, are being rebuilt with seismic expansion joints and reinforced columns. These features let the structures flex and move independently, preventing catastrophic collapse. In Japan, the Akashi Kaikyo Bridge, one of the world's longest suspension bridges, stood firm during the 1995 Kobe earthquake, its design anticipating and absorbing the shockwaves. Water and power networks, often overlooked, are being armored with flexible piping, automatic shut-off valves, and smart grids that reroute energy during crisis. In Christchurch, New Zealand, a city rebuilt after devastating quakes, engineers installed ductile water mains and modular utility networks, systems that bend rather than break when the earth shifts. Even entire neighborhoods are being rethought. Soft soil zones, once prime targets for liquefaction, are reinforced with deep soil mixing, a process that injects columns of cement deep underground to stabilize the ground. In Seattle, critical facilities stand on these engineered islands, shielded from the worst effects of seismic waves. Case studies from around the globe offer proof of concept. In San Francisco, the Transbay Transit Center floats on a bed of isolators, while in Tokyo, hundreds of skyscrapers are anchored with shock-absorbing foundations. Each solution is tailored to local geology, risk profiles, and community needs. Beneath the surface, an invisible web of sensors continuously monitors the pulse of the earth and the health of key structures. When a quake begins, early warning systems can trigger automated responses, closing gas valves, halting trains, and sending alerts in seconds, buying precious time for safety. This is the new language of resilience, innovation, adaptation, and foresight. As the ancient earth reminds us of its power, humanity answers not with fear, but with engineering brilliance, building a future where cities can not only survive the next megaquake, but emerge stronger than before. Beneath the calm surface of daily life, a silent network stretches across the globe, one that listens, watches, and learns from the restless earth. This is the frontier of earthquake prediction and monitoring, where technology offers our best hope for anticipating the unpredictable. At its heart lies a vast array of seismic sensors embedded deep in the ground and spread across continents and ocean floors. These instruments, ranging from simple motion detectors to ultra-sensitive broadband seismometers, capture the faintest tremors, ripples that often precede a major quake. In places like the Pacific Northwest, dense grids of sensors form digital ears, triangulating the origin, depth, and magnitude of seismic events within seconds. But the Earth's story is not written in vibrations alone. High above, satellites orbit the planet, their synthetic aperture radar peering down with millimeter precision. By comparing images taken days or weeks apart, scientists track the subtle warping and shifting of the crust, changes invisible to the naked eye, but sometimes signaling the slow build-up of tectonic stress. These before and after snapshots, processed with advanced algorithms, reveal hidden faults, creeping landslides, and even the slow inflation of magma chambers. All this data flows into the hands of analysts and artificial intelligence, where cutting-edge techniques sift through terabytes of information in real time. Machine learning models trained on decades of seismic records hunt for patterns, clusters of microquakes, unusual ground deformation, or changes in groundwater chemistry that might foreshadow a larger event. In Japan and California, these systems fuel early warning networks, which can detect the first shockwaves of a quake and send automated alerts to cities, factories, and transportation hubs, sometimes before the strongest shaking arrives. Meanwhile, underwater, a new generation of fiber optic cables doubles as seismic sensors, transforming the ocean floor into a giant listening device. These cables detect pressure waves from distant tremors, filling in gaps where traditional sensors cannot reach. Together, these technologies form a multi-layered shield, not to prevent earthquakes, but to illuminate them. The goal is precision, to know, as early as possible, when and where the ground will move. With each quake recorded, each anomaly analyzed, our models grow sharper, our warnings more accurate. The Earth may remain unpredictable, but with technology, humanity edges closer to understanding its ancient rhythms, gaining the precious seconds needed to prepare, respond, and endure. The main shock may end in minutes, but the story of a megaquake is far from over. In its wake, the Earth remains unsettled, its fractured crust continuing to slip, grind, and adjust. This is the realm of aftershocks, a complex sequence of smaller quakes, each a reminder that the ground is still in flux. Aftershocks are not random. They cluster around the rupture zone of the main event, following patterns governed by the laws of physics and the geometry of underground faults. Some strike within hours, others weeks or even months later. Occasionally, a powerful aftershock can rival or exceed the devastation of the original quake, catching communities off guard. But the risks do not end with shaking. Megaquakes trigger a cascade of secondary hazards. Landslides can sweep down unstable slopes loosened by the initial tremor, blocking rivers and threatening to unleash sudden floods. Damaged infrastructure, bridges, pipelines, dams, remains vulnerable to collapse under the stress of repeated aftershocks. Fires sparked by ruptured gas lines or electrical faults may smolder for days, hampered by broken water mains and impassable roads. Scientists track these ongoing threats with relentless vigilance. Seismic networks stay on high alert, their instruments tuned to capture every aftershock, mapping their locations and magnitudes in real time. Satellite imagery and aerial surveys reveal shifting landscapes, hillsides scarred by landslides, coastlines subtly transformed, new cracks and fissures appearing where none existed before. Advanced computer models simulate the evolving stress fields beneath the surface, predicting which fault segments are most likely to slip next. In vulnerable regions, authorities deploy temporary sensors and drones to monitor ground movement, soil stability, and potential dam failures. The flow of data never stops, feeding into hazard maps that guide emergency response and long-term recovery. Even as the initial shock fades from memory, the risks endure. The ground may seem still, but beneath it, the Earth is quietly recalibrating, its silent adjustments shaping the landscape and the lives above for years to come. In the aftermath of a megaquake, vigilance becomes our most valuable tool, and science our guide through the uncertain terrain of recovery.